Okay, guys, let's continue talking about equilibrium. So up until this point, if you guys noticed, when we talked about reactions in equilibrium, they were all in the same state of matter. So if you look back at our old reactions, like everything is aqueous or everything was gaseous, right? Every compound in the reaction, they were all part of the same state of matter, right? So that was all homogeneous equilibria. But now we're going to be talking about heterogeneous equilibria, and that's when the substances are in a different state of matter, okay? So we have an example here. Okay, you guys don't need to write that definition down. You guys should know what homo and hetero mean by now. Hetero just means different, so the compounds in the reaction are in different states of matter. So we're going to be looking at this reaction right here. I do recommend writing this reaction down because this is what we're going to be using as our first example. Okay, so to make sure you guys jot that reaction, PbCl2 is a solid and it is in equilibrium with Pb2 plus ion, which is aqueous, and two Cl minus ions, chloride ions, which are also aqueous. So just make sure you jot down that reaction. And what we're going to do is we're going to learn how to write the equilibrium constant for these heterogeneous equilibria. Yeah, from the total. Okay, so if we take a look at this reaction, right? We talked about when we wanted to write the equilibrium constant, usually we put the concentration of the products on the top, and then we put the concentration of the reactants on the bottom, right? This is just general equilibrium constant stuff. We've been talking about this for a while. Okay. You guys remember this? Okay. Now, the point of this, I guess, part is that when we write the equilibrium constant, the states of matter will matter, okay? So if one of the compounds is a pure substance, which means if it's a pure solid or if it's a pure liquid, we do not involve them in the equilibrium constant. So if we look at this reaction, the tendency might be like, hey, we should put this and this on the top and this on the bottom, right? But if you notice, PbCl2 is a solid, right? So we don't include it in the equilibrium constant. So if we wanted to write the equilibrium constant for this reaction, it would just be this right here. It would be Pb2 plus Cl minus squared, and we don't include the pure substance. We don't include anything that's a pure solid or a pure liquid. Okay, we only include it in the equilibrium constant if it is aqueous or if it is a gas. Okay. It's important to note that PbCl2 is still important. It's part of the reaction. We just don't include it in the equilibrium constant. Okay. All right, so if that's cool, I want you guys to try 12.11 on your own. Just a nice and easy problem to get us started for today. I want you guys to write the equilibrium constant expression for the reaction below. You got H2O liquid in equilibrium with H2O gas. Basically what's happening on the surface of a glass of water. I'll give you guys another minute to finish that up. Alrighty, guys, let's go over this one. Should have been pretty simple. So we said just now that we do not include pure compounds, pure solids, and pure liquids in the equilibrium constant. So if we take a look at this reaction, all we're gonna do is we're gonna write the concentration of the gas, so H2O gas, and this is it. This is the equilibrium constant expression for this reaction. Yeah.
Should we like label it like gas or should we like
No, just leave it. If it's in there, we assume it's gas, and well, H2O can't be aqueous, but yeah. Okay. Okay, so with that being said, I'll give you guys just a couple more practice problems. Try 12.12. There are two reactions. See if you guys can get the equilibrium constant for both of them. Alrighty, guys, maybe 30 more seconds to finish that up. Okay, guys, let's go over the equilibrium constants for these reactions. So the first one, again, we're not going to include the liquid or other solids, so no pure compounds. So it should be products on the top. So it's concentration of carbon monoxide divided by the concentration of carbon dioxide and hydrogen gas. Okay, so that should be the equilibrium constant. And then for the one on the other side, same thing. We're going to exclude the pure substances. It looks like it's solids in this case. So we would have the concentration of carbon dioxide squared because of the coefficient divided by concentration of carbon monoxide squared because of the coefficient. Okay, that's pretty much it. Nothing too difficult. Just remember, if you see a solid or liquid, just exclude it from the equilibrium constant. Okay. Any questions? Alrighty. Now we're gonna move on to 12.13, and this is actually a pretty tricky question that you might see as an FRQ. Okay, so I want you guys to take a look at it. I'll kind of explain what's going on, and then I'll have you guys try it on your own. I'll give you 4 minutes to do it because it does require some thinking, and I want you guys to write your explanations for why you got your answer, okay? So it says that each of these mixtures are placed in a closed container, and you just allow it to basically go to equilibrium if it can. So you got a container. In part A, it's saying that you put in only solid CaCO3, and then it's asking, will this go to equilibrium? Okay. In B, it's saying that you put a solid CaO and you put CO2 gas. The pressure is greater than the equilibrium constant for pressure. Will this go to equilibrium? Okay, so we're combining a lot of different concepts here. So I'll give you guys 4 minutes to try that out. I recommend talking it through with the person next to you. See if you guys can write the justifications and get the correct answers. Will each of these scenarios go to equilibrium? And if so, why? Okay, so try that out, guys. Give you guys 4 minutes, and then we'll go over the answers, see how well you did. Hey, this is a tough one. You got to combine a lot of different concepts we learned. Okay, so let's start with A. Okay. I was gonna ask who said yes and who said no, but I feel like the further down we get, the less people would participate. So I'm just gonna go over it, okay? So for A, we have a container, and then we just have solid CaCO3. Okay, and we learned before that if we have one, it doesn't matter if we have the reactants or we have the compound or products, eventually CaCO3 will decompose to produce CaO and CO2 until it gets to equilibrium. So for A, the answer is yes. It will go to equilibrium because CaCO3 will decompose into the products. Okay. Yeah, no, super simple. Okay. My philosophy in life is KISS, K-I-S-S. Keep it simple, stupid. Okay. Just remember this, guys. If you learned anything in this class, the smartest thing you could do is not think. Dumb people need to think, but smart people just do because they already know. Okay. Same thing with studying. Smart people don't need to study because they already know. This horrible advice that's being recorded right now. Anyway, moving on. Okay, so container B. Okay, it's telling us that we have CaO solid and we have CO2 gas, and the pressure is greater than the Kp, the equilibrium pressure, okay? Now, if you guys notice, CaO and CO2 are both what? Okay, yeah, they're in their state of matter, but again, keep it simple. What are they? Yes, they're both products. Okay, yes, they are in their state of matter. They are matter. Okay, so since they're both products, what are they gonna want to do? Yeah, they're going to want to synthesize into the reactant. And it'll be even easier for them to do that because look at the pressure. The pressure is greater than Kp. If we go from if we turn some of the gas into solid, what's going to happen to the pressure? Yeah, if we get rid of some of the gas, the pressure will go down, which is what you want because you want to get to the equilibrium pressure. So the answer for B is also yes. Okay. Now, if I wanted to, I guess, elaborate or write that out, because I think you guys might want to write this down, you can say that the products are going to want to turn into the reactants. Okay. The pressure wants to decrease. Okay. And so if CO2 gas becomes CaO-CO3 solid, the pressure is going to want to decrease. Okay. So that's the answer for B. It is also yes. Any questions on that one? That one a little bit more complicated, but kind of not really. Okay, let's move on to C. Okay, in C, we have CaCO. Oh, why am I doing it like that? Okay, we have our container. And then inside we have the reactant CaCO3 solid. And then we have CO2 gas. And then the pressure is greater than the Kp. Okay. Okay, so if we take a look at this, I'll just give you the answer right off the bat for this one. This one is going to be no, it will not reach equilibrium. Okay, and the reason why it will not reach equilibrium is because if you notice, what do we have inside the container? We have the reactant and we have the product, right? Now, if we just look at it very simply, CaCO3 can decompose into CaO and CO2, right? But if you look at it, CO2 cannot turn into CaCO3 because it doesn't have CaO, right? So you might be wondering, hey, wouldn't CaCO3 just make some CaO so that it could react with CO2? It will not, because if CaCO3 decomposes into the products, what's going to happen to the pressure? Yeah, the pressure is going to go up because CaCO3 will produce a gas. If there is more gas, it's going to increase the pressure, but the system does not want to increase the pressure. It wants to go down. And so those are the two reasons. The first reason is that there's no CaO to react with the CO2, and the system does not want to increase the pressure. So it's not going to want to turn into CO2. Those are the two reasons this one will not go to equilibrium. Okay. Are they saying LeBron James?
Old team.
Is it? Oh. I feel like I should know it. Okay, let's move on to D. Last one. Okay, last container, we have CaCO3, which is a solid, and then we have CaO, which is a solid. Okay, now for this one, the answer is yes, because CaCO3 is going to decompose into CaO and CO2. CaO doesn't do anything. It's just chilling. Okay. And that's it. Anyone get all of them? 3 of them? 2 of them? Oh, 1 of them? 0 of them.
Yeah.
It's okay. It's okay.
I thought it would be something way different. I didn't think it'd be like yes or no.
Determine whether or not it can attain equilibrium.
No, yeah, I hear me out, but I thought like the explanation part, I was like, yeah, I don't know how to explain it.
Josh, you're thinking too much. Stop thinking, okay? Thinking is for dumb people, and you're not dumb, okay? But if you think more, you will become dumb. Hold it. Okay, so those are gonna be the answers. So this is another way to think about equilibrium. I'd say the toughest two was this one, B and C, just because you had to consider the pressure, and that kind of adds another dimension to it. But hopefully this was a good explanation of that. Okay, we are going to skip 12.14 because it's the same thing we've been doing, just writing the equilibrium constant. And then now we are going to get to my favorite part, the math. Okay. I'm gonna try to make jokes. We're talking about gases, so I'm trying to like put fart in somewhere, but I really can't. But if you guys see an opportunity to tell a fart joke, please do. Because everyone thinks it's cringe, but everyone does end up laughing at it, okay? Because it's a universal condition. Everyone has had a nasty fart, held in a fart, felt the pain from holding in a fart. So anyway, okay. So if we can get the equilibrium concentrations for reactants and products, we can calculate the equilibrium constant. It's pretty simple. You just plug it into the equation, okay? And that's what's going to give us the equilibrium constant value. So let's go straight into 12.15. I want you guys to just try solving it, okay? Okay, it's asking us to calculate the equilibrium constant Kp for the reaction below. It gives you the pressures of everything in it. So I want you guys to calculate Kp. This one should not be too bad. I'll give you guys a minute and a half to try it out, and then we'll go over it together, okay? So I would recommend write the equilibrium constant or the equilibrium constant equation, and then plug in your values afterwards. Okay, that's probably the easiest way to do it. Give you guys a minute and a half. All right, you guys ready to go? Yes? Okay, let's go over this problem. So this one should not have been too bad. Like I said, you want to write the equilibrium constant expression. So what we're gonna do is we're going to write the expression for this reaction. Everything's a gas, so we don't need to worry about any pure substances. So the equation is gonna look like this. You'll have the concentration of ammonia on top. Make sure you squared it. You'll have the concentration of nitrogen gas on the bottom, and then hydrogen gas on the bottom, and make sure you cube it, okay? And if you guys forgot the exponents, don't worry. I probably would have forgotten to if I was taking AP Chem. There's just too much stuff going on, okay? I don't know, but you guys are smarter than me, so maybe you guys would have got it. Okay, anyway, we're gonna plug in the pressure for NH3, which is gonna be 0.166 atm, and we're going to be squaring it. We're going to plug in the concentration of N2, which is 2.46. And then we have H2, 7.38, which we will also, or we will be cubing. And then so your final answer, you should have gotten 2.79 times 10 to the negative 5. Okay, something closer. 2.8 is fine as well. Yeah. No, for equilibrium constant, there's no units. Good question though. Oh, and it's not KC, sorry, it's KP. All right. Dude, what happens up there all the time? It's like they're always moving.
Oh, it's meant to stay.
Yeah.
That section.
Is that why the desks always move?
I think so.
Oh, that makes sense. You know what? But I understand. The people underneath me have to listen to me play basketball all the time. So they're probably wondering what's going on up there. Okay, let's move on. I'm gonna have you guys try 12.16. This one's gonna be a lot of practice with scientific notation. So hopefully it's good practice for exponents. So I'll give you guys a minute and a half to try this one as well. And then we'll move on to, I guess, the most important skill for this unit. So everything that you've done has been building up to this moment. 12.17. So try 12.16 and then we'll go over 12.17 together. Let's see how you guys did on that one. So the formula for this one should not have been too difficult, especially since we don't have any exponents. The hardest part was just working with the exponents and doing the math. So let's see what you guys got. So for the equilibrium constant equation, we just had to put CH3COO minus on the top, and then acetic acid on the bottom. I forgot something, and then H plus on top as well. Okay, so on the top, we'll be plugging in 5.44 times 10 to the negative 4, and then we'll be plugging in 5.44 times 10 to the negative 4. So you could have squared it if you wanted to. Whatever's comfortable with you guys, but I know some of you guys like seeing everything spread out, so I'll just leave it like that. Okay, and then we'll put 1.65 times 10 to the negative 2 on the bottom. And I love saying this because I got beat up for saying it when I was a kid, but according to my calculations, 1.794 times 10 to the negative 5 is what I got. Okay. Guys, you guys have it so lucky nowadays. It's cool to be a nerd now. It's cool to be smart and play video games and stuff. I got wedgies for that when I was a kid. We just went out. We played outside a lot. That's what I noticed a lot of like kids nowadays don't do. Yeah, we played outside a lot. The dumb stuff. We went exploring. I would ride my bike like at least a good like 10 miles a day during the summer. Yeah, just going around. But I was still fat for some reason. That's the weirdest thing. Like, how's that? How? Like, it doesn't make sense. Genetics, dude. My genetics suck. I had no chance of making the NBA. Anyway, let's move on. Okay, so this is, you guys, please don't write this down. This is just me having it written for you, just so you can read back at it. But basically, the point is, oftentimes we don't know all the equilibrium concentration. So you know how in these problems so far, I gave you all the concentrations for everything in the equilibrium reaction, right? But a lot of times you do not know the equilibrium concentrations. And on the AP test, they will most likely not give you all the equilibrium concentrations. And so you gotta figure it out, okay? And so to figure it out, we use something called an ICE table, okay? And so I do want you guys to write down a couple things here, okay? And I'll highlight what those are. Okay, so in an ICE table, just write down that I stands for initial concentration, okay? So again, please don't write everything down. This is all online for you. I put my heart and soul into writing this. And so you guys can go look at it, but just write down the parts that I'm highlighting. Okay, in an ICE table, I stands for initial concentration. Okay, basically what concentration is everything at in the beginning. Okay. Next we have C. C is change in concentration. Okay. So how does everybody's concentration change during the reaction? Does it go up? Does it go down? So basically it could be a positive change or it could be a negative change. That's important too. And just a heads up, this is when math is going to get really fun. And this will really show you how well you know algebra. Yeah.
Remember how you told us that one of the equations was like derived from calculus?
Yes, the instantaneous.
Oh,
Did you?
yes,
You did? The instantaneous rate? Yeah, it's just you find the derivative of the point. Okay. I don't know. Oh, PTSD. Okay, so E is the concentration when the reaction is at equilibrium. So ICE. Okay. Ice cream, excellent. Okay. Equilibrium. So everything is for concentration. Initial concentration is I. C is change. E is equilibrium concentration. Okay. Okay. So you guys know what all the parts of an ICE table stands for. And now we're going to learn how to use an ICE table. It's a lot of fun, guys. You guys are going to love the math. Do you guys remember the quadratic equation?
No, yes, sir. Stop.
Oh, if you remember, you are in great shape. If you don't worry. I'm going to teach you a song. There you go. Did I teach you that already? Oh. My 8th grade, my 7th grade Algebra 1 teacher sang that to us. And I literally never forgot it. It's incredible. Thank you, Mr. Anderson. Mr. Anderson. Okay. Huh?
Listening right now.
He is. I hope so. I wonder if he's still working. Kind of old. Okay. Let's move on to 12.17. So now we're going to use an ICE table. I have a link right here if you guys want to use it to read more about ICE tables, but kind of already. We're going to go over how to use it. But if you want some extra reading. Okay. So please don't write all this down. All I want you guys to do right now is write down this equation, but write it kind of spaced out. Okay. Put some space between all of the compounds. So I'll put a space right here, a space right here, space right here, and a space right there. So space it out because we got to create an ICE table underneath it. Okay, just write down the equation for now. And then we'll go over what we have to do. Okay, so what we're gonna do, guys, is we're gonna create an ICE table underneath our equation. So I'm gonna write I, C, and E. And then what we're gonna do is we're gonna draw a line across, another line across. Hopefully your line is straighter than mine. And then we're gonna separate the different compounds as well. So something like that. Okay, so this is an ICE table. And I will show you the beauty of how to use an ICE table. You will cry with joy because of how beautiful it is. Or you might cry for another reason, but. Okay, so ICE tables are really, really easy to use. Okay, we're gonna start with the first row, okay? We just go top to bottom. Okay, what we're gonna do is we're gonna write the initial concentration for all of the compounds. So this is a fake equation, obviously X, Y, Z. And so if you look at this, there's 0.5 moles of X in the beginning of the system. The volume is not gonna change in this reaction, so we can just use the moles. So we can write that there are 0.5 moles of X. Okay, usually we do concentrations, but if the volume is constant, we don't need we can just use moles because the ratio will stay the same, okay? So we start with 0.5 moles of X, okay? In the beginning of the reaction or system, that's what we have. Okay, and then it tells us at equilibrium, the amount of sample X is known to be 0.35. So that means we started initially with 0.5 and then we end up at 0.35 moles. Okay. So far, so good? Okay, so it doesn't say anything about the product, so we can assume that we started with no Y and no Z. So we're going to plug in zeros there. Okay, and that's all the information that's given to us in the problem. Okay, now we just need to start filling in the table. Okay, any questions where we got these numbers? That's good. Okay, so we basically finished the initial row, so let's go to the change row. Now, if you take a look at this, we started at 0.5 and then we ended up at 0.35. How do we find the change? Yeah, final minus initial, right? Again, keep it simple. Okay, 0.35 minus 0.5. So our change was negative 0.15. Okay, very easy, right? Okay, however, there is something that you guys need to keep in mind, and it's the coefficients. Okay, if you take a look at this reaction, what this reaction tells you is that in order to make 3 moles of Y and 4 moles of Z, you need to lose 2 moles of X, right? What that means is that the change in X is 0.15 moles, and that is equal to 2X. Okay. Okay, actually, sorry, I'm not going to use X just because it's a weird variable. We already have an X here. We'll just Z, we have a Z. Why do you want to C? Oh, change. Okay, we'll use 2C, okay? Okay, so if we solve for C, C is going to be 0.075 moles, right? I think. Haha, yeah, 0.075. So basically what this is telling us is that every time we lose 2 moles of X, we're going to gain 3 moles of Y and 4 moles of Z. Make sense, guys? Okay, what that means is as we lose the reactant, we are going to produce product and we're going to get plus 3C, 3 moles of C, and plus 4 moles of C. Okay, so again, this reaction is telling us every time I lose 2 moles of X, I'm going to get 3 moles of Y and 4 moles of Z. So basically, C just represents 1 unit of measurement as we go into the equation. Okay, so all we need to do is multiply C, which is 0.075, by the coefficient. So for Y, it's going to be 3. So 3 times 0.075. So that means we're going to have an increase of plus 0.225 moles. Okay, so Y is going to increase by 0.225. And then Z is going to increase by 0.3 moles. So far, so good? Okay, so if we increase by 0.225 moles for Y, what's the equilibrium amount? Yeah, 0.225 because we started at 0, right? So it'll be 0.225 moles and 0.3 moles. So that's how you use an ice table to find the final concentration of all of the compounds in your equilibrium reaction. Okay, and now that we have all of the equilibrium concentrations, we can plug it into the equilibrium constant reaction or expression and calculate it out. So I'll give you guys some time to do that, but same thing as before, the equilibrium constant expression is the same. We're gonna have the concentration of Y cubed, the concentration of Z to the power of 4, and then the concentration of X squared. All we need to do is plug in these equilibrium concentrations, and that'll give us the Kc. Yeah, what's up? So we looked at, so from here, we looked at the information they gave us from initial to equilibrium, right? The difference from 0.5 to 0.35 is 0.15, right? Now, 0.15 is the change when you lose 2 moles of something in the equation. And so if we just want to find 1, we just divided it by 2 to get 0.075. Since you get 3 moles of Y for every 2 moles of X that you lose, all we needed to do was multiply the base, the C, by the coefficient by 3. And that's where we got the change in Y. Same thing with the change in Z, except that it's 4 instead of 3. All right, so if we start plugging in the values, if you guys started doing that, that's great. You guys are going to plug in 0.225 for Y, and then you're going to cube it. You're going to plug in 0.3 for Z to the power of 4, and then X is 0.35, and you're going to square it. And according to my calculations, you guys should get 3.17 times 10 to the negative 3. Okay, you can also write that as 0.00317. Okay, they're the same number. You guys all get that? No, something else? Oh man, I might be tripping. Let's see if Mr. O is crazy. Okay, so 0.225. Dude, I need a better calculator on this. Freaking Windows 7, 0.225 times 0.225. Okay, that's what we get. Okay, our value's gonna be so messed up now. Okay, so for Y, you'll get 0.011. I'll round to 4. Okay. For Z, 0.3 times 0.3 times 0.3 times 0.3, and then that's what you'll get. 0.0081. And then on the bottom, we'll get 0.35 times 0.35, and then that's what you'll get on the bottom. Okay, so I don't want to round, so I'm going to do 0.25 times 0.5 times 0.5 times 0.0081 divided by 0.1225. What the heck did I get? Who did this? This wasn't me. I'm blaming Peak. Okay, yeah, so I was wrong. You were right. 7.532 times 10 to the negative 4. First try. I told you guys it was 7.5 times 10 to the negative 4. Come on, everybody. I think I didn't multiply by 2. Okay, but makes sense, guys? Ice tables, pretty fun, right? It's a lot of fun. Algebra is great. All right, so I'm gonna give you guys some time to practice. Actually, let's take our first break right now. We'll take a 7-minute break, come back together, and we'll see if we can squeeze in 2 ice table problems, and then we'll, I guess, end after that. Okay, so take a 7-minute break, stretch your legs, go to the bathroom. Okay, guys, let's have you guys try another ice table problem on your own. We're gonna move on to 12.18. The hope is that we'll finish 18 and 19 today, and then so you don't have to do any quadratic equation problems today, but next week we'll do our quadratics. Anyway, I want you guys to try 12.18. Draw your ice table. I'm not really going to be helping you here. So let's see how well you guys understood it last time. Please make sure to look back at your previous example, just so you have a reference. But yeah, use an ice table, and you're going to be calculating Kc for the reaction down here. All right. Good luck, everybody. I'll give you guys like 5 minutes to try this out. Okay, guys, let's go over this problem. So I have the ice table set up with the information that's in the problem. This is what you should have just copied down. Everything else from here is going to be a calculation. Okay. Before we go on, any questions on where we got these numbers? Okay. All right. First thing you want to do is figure out the change for HI, because that's the only one you have the equilibrium value for. So obviously this is going to be plus 1.87 times 10 to the negative 3. Now, if you guys notice the coefficients, it's going to be 2 for every one of these. Okay, which means that here we're going to have 1.87 times 10 to the negative 3. The change is equal to 2. I'll do x this time because we know what x is. X is going to be the base change. And so x should have been 0. What the heck am I doing? 0.935 times 10 to the negative 3, or if you wanted to go scientific notation, 9.35 times 10 to the negative 2. Okay. So that means we're going to increase by a factor of 0.935 times 10 to the negative 3. Again, if you got this 0.12935, that's fine as well for both of these. I'm keeping it -3 so that the math here is a little bit easier to work with. But for your equilibrium values, you should have gone 0.065 times 10 to the negative 3 and 1.065 times 10 to the negative 3. Yeah, what's up? (9.35 times 10 to the negative 3?
Oh, it's just the decimal. It's the same time.
Anything else is wrong then? Actually, that does make sense. No, because you gotta divide it by 2. So it should be 9.35 times 10 to the negative 4, not negative 3. Yeah, I set it as -3 just so we can work at this better. But if you wanted to keep it scientific, it should have been 9.35 times 10 to the negative 4. It doesn't make sense for it to be -3 here because it's basically 18 to the negative 4, so it should be 9 negative 4. So yeah, double check your calcs. But yeah, this should be your final concentrations. If you guys want to convert it into pure decimal form, it should be 0.12345 and then 0.121065. This should be your number. So whatever exponents you got, convert it into decimals. That's what you should get for your decimals. Okay. Because you need to divide this by 2. That should give you 0.9 times 10 to the negative 3. Yeah. Okay. So we're gonna plug it into the equilibrium equation now. So Kc is going to equal the concentration of HI squared, and then we'll have the concentration of H2 on the bottom, the concentration of I2 on the bottom. We plug in those values. You should have 1.87 times 10 to the negative 3 on the top squared. On the bottom, you'll have 0.065 times 10 to the negative 3 times 1.065 times 10 to the negative 3. And then for your final answer, you should get something close to 51. If you got 50.8, 50.9, that should be good. But your final answer should be 51. Close to it. Okay. Yeah. So which one? The equilibrium? Yeah. So what we did was we started with this one and that one, the blue ones, right? So what we did was we calculated the change, which is going to be 1.87 times 10 to the negative 3, right? Now, if you notice the coefficients, you need to get rid of 2 of these in order to make 1, right? And so what we need to do is divide it by 2 in order to get the change for these ones, because the ratio is 1 to 2. And that's why we divided the change of the product by 2 in order to get the change of the reactant. Okay, make sense? What E? For these guys? Oh, you just need to add it. So 1 times 10 to the negative 3 plus 0.935 is going to equal this. So plus them together right here, and then plus them together. Okay, let's. Oh wait, sorry, subtract. My fault. Subtract. I'm crazy. It's subtract because you're going from left to right. I'm sorry. So subtract.
Okay.
Yeah, subtract. No, because because we're going from right here, if you notice, we're going from 0 to 1.87. So this one has to be the positive change. These guys have to be the negative change because, yeah, you're trying to go to equilibrium. My fault. I did a bad job explaining it. Thank you for bringing that up. Yeah, so the reason why these two on the left side are negative is because you're going from 0 to 1.87. So you're adding, you obviously need to increase. And so these guys need to decrease in order for the product to increase. Okay, sorry about any confusion, guys. Any other questions?
No, I was gonna say that threw me off.
Yeah, that's my fault. I did a bad job explaining. I'm sorry, guys. Okay, we'll actually close it up there since we are almost out of time. If you guys want, I would recommend going on into your homework and finding an ice table problem, just trying it out, just so that you guys have a refresher during the weekend. Because when we come back, we're gonna combine this with the quadratic equation, so the math is gonna get a lot harder and longer. So I would recommend at least over the weekend, just doing at least 1 or 2 ice table problems. Just so that you guys can get some practice in, so you guys don't forget how to do it. Okay? Yeah.
For the assignment, homework 11A, there's a thing there.
Oh, check the tape. Just check the schedule on the Google sheet. Yeah, what's about? No, not for ice tables. I'll show you. You'll see why we need to use. Yeah. Why the reason we need to use a quadratic is because it's because of these coefficients. You'll see next time. It's easier to show it than to explain it. All right. All righty, guys.